Hello everyone, let's find out electric potential due to a point charge. So let's assume that there is a point charge called as capital Q, and this point charge is placed at a point A. Now let us try to find out what is the potential because of this point charge at a given point B such that distance between point A and point B is R. Now our aim is to find the potential at this point B. By definition of electric potential, the electric potential at a given point is the work done in bringing a unit positive charge from infinity to that point. Let's assume that this is the charge Q and this charge is being brought from infinity. Now this charge would come closer and closer towards this point B. Let's assume that at a given point of time, this charge Q is somewhere at point C, such that the distance between this point A to point C is some x. So apparently the distance of this point from this charge is C. Keep in mind that this x is a variable. C is the point and x is the distance. This x is a variable. If the point C is at infinity, then x tends to infinite. If the point C is at point B, then x becomes R. R is the fixed distance. Now let's assume that we move this charge by a small distance from point C to point D, and this distance is very small. Let us call it as dx. Now dx is a very small distance. Now here we are doing work because both capital Q and small q has same polarity. Therefore capital Q would push small q away. So we should do work to bring it from point C to point D. That work done by us, it is called as dW. dW is the work done to move the small charge Q from point C to point D, and work done is equal to F into dx. This F is a force which is applied by us. So I'll put F suffix A. Here the applied force and the moment are in same direction. So F suffix A is the applied force by the external agency. Now we don't know what this FA is, but at the point C, the reason we apply force here is to counter the force of repulsion between two charges. That is, when the charge is at point C, capital Q would push it away, and that force is called as Coulomb force. So that Coulomb force is equal to 1 by 4 pi epsilon naught, and then it will be capital Q small q by, it's at the point C, so distance between point A and point C now is x square. But recall that 1 by 4 pi epsilon naught is equal to k. So therefore the Coulomb force is equal to k capital Q small q by x square. So the force what we apply here, this applied force should be at least equal to the Coulomb force. To make sense out of it, think of a case where there's like a box, and then imagine that its weight acts downwards, and that is say 20 Newton. Example, suppose if we want to move this box from here to some distance, the applied force, which is Fa, this applied force should be at least equal to 20 Newton, otherwise the block will fall downwards. So this applied force is equal to the Coulomb force with different directions. That is because the applied force is like this and the Coulomb force is like this. This is a Coulomb force. Therefore they'll have opposite directions. So putting it back here, the work done is equal to minus of k q by x square into dx. This is the work done to move from point C to point D. So if we want to find the entire work done, then we can assume that each time we move a small distance. So the work done here is dw, dw here, dw, dw. So for every small displacement, some work has been done. That is called as dw. Therefore, we can say that the total work done is nothing but adding all the small work done. So that will be integration. That will be adding all the small work done. That is equal to integrating k q by x square dx, and here the variable of integration is x. Now by definition, to define electric potential, the charge is being brought from infinity. So x starts from infinity, it's from infinity to the point B. So when the charge is brought to the point B, the distance becomes r. So this is the limits. Therefore, the work done here, in this case, minus k capital Q small q comes out, they are constants, and what is left out is integral of x power minus 2 dx to the limits r to infinity. And recall x power n dx, that integral of this is equal to x power n plus 1, that is equal to minus k capital Q small q x power minus 2 plus 1 by minus 2 plus 1. The limits are infinity to r. Minus 2 plus 1 is minus 1. So this minus 1 cancels, and what remains here is, it will be k q by, this term here is x power minus 1, that becomes 1 by x. Limits are infinite and r. Let's put the limits back now. That is equal to k q 1 by r upper limit minus 1 by infinity, and this term tends to 0. So finally what we get here is, it will be k capital Q small q by r. This is the work done. But by definition, we want work done per charge or per unit charge. So the charge moved is small q. Therefore, work done by small q, which is the potential, is equal to k q by r. So this is the electric potential at a given point, is equal to 4 pi epsilon naught q by r. So this is the form of potential. Keep in mind here that since V is a scalar quantity, in case of potential, we put with its polarity. That is, from charge of minus q, think the charge is minus q, then for that charge minus q, the potential I call it V dash, that is equal to minus k q by r. So the potential could be positive or negative also. Now when you want to add the potentials, then that will be just sum of each potentials. If you have more than 2, you'll add up with each potential. Now from expression given here, V is equal to k q by r. From here, as r tends to infinity, V becomes 0. So potential for a positive charge would keep on decreasing. So it is highest very close to the charge and keeps on decreasing. Similarly, for minus charge, the potential keeps on increasing because it is negative. So potential for minus charge increases and becomes 0 at infinity. And here, from a given point charge, for a given distance, it will have same potential without direction. The reason that we took potential is because it's a scalar quantity without any direction. So for given charge, it will be spherical symmetry. That is, from a given point charge, every point will have same potential and those points will lie on a sphere. As seen earlier, a positive charge gives rise to positive potential because V is equal to k q by r. A negative charge gives rise to negative potential. That is because for negative charge, if you call the potential as V dash, that is equal to minus K Q by R, it will be negative. And potential of Earth is 0. That is because Earth is a huge reservoir of charges. You can think of Earth as a huge. So Earth contains a lot of charges. So if you put this as plus charges, there will be equal amount of minus charges, so that the net charge adds up to be 0. For the Earth, the potential is always 0. Now we have seen that in buildings we connect a earthing point so that excess charges flows into the earth. Now you can understand this, even after the charges flows, the Earth's potential is almost 0 only. Why is that? To understand this, we can think of the Earth like an ocean. Now from an ocean, whether water is drawn, that is, if small amount of water is drawn from the ocean, or if water is dropped into the ocean, its volume will not change much. Similarly, when a small amount of charge leaves from the Earth's surface, or when charges is added to the Earth's surface, in both the cases, the Earth is so huge that the addition or subtraction or removal of some charges will not alter its potential much. Therefore, for the Earth, the potential is always 0.